Good afternoon, everyone. Thank you for joining our ODIN webinar. I see we've only got 3 attendees out of the attendees list at the moment, so maybe just give a minute or so just to let another few people join. I know there was a few more people had signed up. If that's okay, we'll start in just a minute's time. There's more people coming in now. We've got a few more attendees now, so I think we'll just make a start on the essence of time constraints, and then we'll, if anybody else joins, that's fine. Good afternoon, everyone. Thank you for joining the ODIN webinar. My name is Peter Taddy. I'm Innovation Delivery Project Manager at SSEN Transmission. I'm joined today by my colleague Kevin McDonald, who's HVDC Operations Engineer at SSEN Transmission as well, and being supported by Marcela Jara, Project Manager for Ross Robotics, and Dominic Tusk, Managing Director of Ross Robotics. We have a short presentation today to talk to you about the work that we've done in the ODIN Discovery Project, and then there'll be a chance to ask any questions at the end by raising your hand. So we'll just move on. Within the ODIN Discovery Project, we've completed a 3-month SIF discovery project, which has been delivered using strategic innovation funding, which is governed by UKRI. As SSEN Transmission, we were the lead partner on the project, and then supported by Ross Robotics, who have done the bulk of the work on the project. ODIN builds on the previous project that was delivered using the Network Innovation Allowance, so NIA funding, which was called Aim High, where we deployed an autonomous robot within an HVDC valve hall. At the moment, data that's being gathered by that robot is manually reviewed, so it's a very labour-intensive task for people like my colleague Kevin to review any of that information and the data that's being gathered by the robot. With that, you have no trend analysis, and we also have the potential that something could be missed when you're trying to review large amounts of data. So within the ODIN project, we identified that there was a gap there, and we've successfully delivered a proof of concept with AI and machine learning, which will enable automated interpretation of that data that's being gathered by the robot. The benefits of that are enhanced reliability, efficiency and safety, while also reducing the cost and improving the overall operation and maintenance of our HVDC systems. Largely that contributes to the acceleration towards a net zero energy network. It's a brief introduction to the project. I'm now going to hand over to Ross Robotics, who will talk to you about some of the more exciting work that's been undertaken within this discovery project. Marcela? Dom?
Okay, so I'll jump in here. I think the first point that we would like to make is just what an extreme environment the robot is deployed in. So we have very high levels of electromagnetic interference. Clearly, with such high voltage equipment, there is a risk of flashover, and also very high temperatures, all of which are really not great for for complex electronics. Another sort of unique stress, I would say, to this solution is the fact that we can't be hands-on with the robot for periods of 12 months. So when the robot is deployed, the hall is closed, and that's it for 12 months. And that's a very unusual scenario for a robot deployment to not be able to go anywhere near it for a 12-month period. The physical configuration of the halls is also challenging, with key components at heights of up to 12 meters. And often shielded by corona shields, making it difficult to get clear pictures of everything that we need. So within the hall at this point, and I just add that this is globally, these robots are the only robots that are deployed in live HVDC environments. So it's very much a sort of a new and innovative, approach that we're taking here, and we're capturing data that's never been seen before, and identifying conditions that are really starting to give us, I think, a new level of understanding and insight into what's happening within this critical infrastructure. The discovery phase has identified real potential for reliable condition monitoring, and ultimately, what we hope was that we'll be able to start predicting, failure. So predictive failure identification and maintenance, and that, I guess, is the sort of the ultimate goal for us here. What does all of this mean? I think what it means is that we can offer and transform the level of reliability of this critical infrastructure. And what that does is that obviously delivers improved service and efficiency for consumers and suppliers. Okay, if we go on to the next slide, and I'll hand over to Marcella.
Thank you, Dom. As Peter and Dom have mentioned, there is a lot of data that's collected. We've got robots roaming around the live HVDC halls, stopping at several points along the path and taking images of key infrastructure. We're collecting a variety of data, so thermal images, optical images, UV. We have a UV camera that's spotting discharge, corona discharge, and we have audio as well as environmental sensors. So lots of data for somebody like our good friend here, Kevin, to look through, and lots of alerts that he's going to be getting from that. So to get to a point where we make life easier for the HVDC operations managers and for other staff, we wanted to enhance this platform that we've created called, the project is ODIN. We are called ADA, our AI data analytics platform. And in order to make that useful, there's a couple of steps along the way. We had a minimum viable product version of the platform that we've really enhanced during this discovery phase, and there were 3 key points that we needed to get moving. So getting the data from the robot up to the cloud, so that it can be accessed from anywhere. And there's lots of data that it's collected. The robot goes around the hall once a day and stops at multiple points. So every inspection, there's new data and large amounts of it to deal with. We want jumping to the end, a user-friendly interface so that you can browse through the data in all directions. You want to move through the data historically, moving through the different data at the different inspection points, through the different tasks, so that we need to find a good way to be able to browse that data in a timely manner and an easy to understand way. And the final part, but possibly the most important, as we're aiming towards the end goal, as Dom mentioned, of being able to predict potential problems. The first step along that route is to be able to identify components with which we can pull out information about. So we've managed to achieve these three things to be able to take us to the next level and look to the future. Next slide, please. So this is a little bit about how the different pieces of the puzzle look. We've got the robot driving around the hall. It's connected to a network. It's got a little base station where it can go and charge while it's not in use. And all of that information is pushed up to a computer in an OCU, the operator control unit, that's sat in the control room of the HVDC hall. So from here, we can set up different inspections as well as do impromptu inspections when something interesting is found. And what we want to do now is push all of that information up to ADA so that it can be stored centrally and accessed from anywhere. Next slide, please. Thank you. So this is a little bit of what the ADA platform looks like now. A very beautiful view of a cable ceiling end. The colors actually represent different temperatures. This was taken from a thermal camera. And that was the area that we were focusing on for the discovery project, that where we thought we could make a big impact quite quickly we were using the ADA platform to first of all be able to see where in the hall this was taken. So you can see a little representation of a robot next to the on the map, and a image of what was taken at that point. As I mentioned, we had a minimum viable product. This was enhanced. So on the right hand side, you can see a slightly different view of the data, where it's a single inspection point, but all the different data points that were collected at that part. And the way we designed the improvements to the user interface was really through lots of discussions with our colleagues here from SSENT, and really understanding what we needed to do to make this information valuable. Understand how Kevin goes around troubleshooting potentially a problem, what things are of interest to them as a company and as a business, and how we could bring that to the forefront and make this platform useful in the first step, as well as how to enhance it for the future and continue providing additional value. Next slide, please. So the first piece to this is really the fundamental part, which is getting the data off the robot, out of the HVDC hall and up to the cloud. So at the moment, the robot pushes the data up to the OCU, the computer in the control room, and then we needed to create a standardized and efficient way of uploading information, potentially large amounts of information, over the network up to the cloud, and from there be ingested into the cloud platform and stored in a suitable manner in the database so that it can be accessed quickly and stored according to the right inspection points and the right dates. So that involved creating an API that allowed that information to be uploaded. And it means that now that this has been completed, first of all, we had quite a large amount of data that was just sat waiting to be uploaded, and actually we did it all in one batch, so really stress testing the API, and we uploaded hundreds of images from several hundred inspections that we performed before this project started. And now that it's completed, the robot can push that automatically up to the cloud platform, and the data is relatively live. So once the inspection is completed, the data is uploaded. Very short time after the inspection is done, it can be looked at and inspected by the HVDC operations team. Slide, please. And here we get to the really exciting bits. This is on the left is an example of an image that we get from the thermal camera. What we decided on through all the discussions with SSENT was that this was a key component that we wanted to look to identify. It was something we were interested in understanding more about, how it was, what the temperatures are, so we can try to identify any problems with it. So as I mentioned, the first step is finding it automatically in the image. Obviously we can look at it and see that it's there, but we had to develop an AI model, a machine learning model, that we showed lots of different examples of this image, so from different angles, from different orientations, so that we could show it how to find it on its own. So once we developed and designed the model and trained it using a small data set to see how it would perform, we ran the model against this large collection of images that it had never seen. And it's like having a small child. We were all very proud when the first time it came out and said, this is a cable ceiling end, without anyone having interfering in that information. So this is 2 images that really show a huge amount of progress. When it was able to, with quite a high level of certainty, declare that this was the cable ceiling end, it means that we've proved that this is something that is possible to do. Once the model has identified that component, we can then start to pull information out of it. So while it looks like a picture, it's actually got lots of data in the background. Each pixel has a temperature associated with it. So once we've identified that specific area in the image, we can pull out the temperatures in the background and start to do clever things with it. What's the maximum temperature we've seen of it? What's the minimum temperature? What are the average temperatures? And then how is that temperature varied over a period of time? So those are the next steps we're looking to do. If you look at the next slide, please. This is a little bit about the process that we defined and have been using to get to this point. It was the final step was to show it all these unseen images and let the model identify the component. But we had to, there were several steps along the way testing what the right model would be, labeling the data so we could create a test set. So lots of different examples of what the cable sealing end looks like so that the model can learn and then go on to identify it on its own. So we went through this loop in the middle several times, trying to make the model better and better. And we've come to, at the end of the project, we came to a point where we were confident that we can take this further and start to use it for other key components, hopefully in the next phase. Thank you very much. And we'll move on to the next slide and I'll hand back to Dom.
Okay, so I think having had a very sort of strong result from the discovery phase, the plan now obviously is for us to move on to to the alpha phase, and really the main focus there is going to be building on the proof of concepts that we that we've identified in the discovery phase, and delivering something that is usable for SSEN. The main sort of focus for that is that there's an intention within SSEN to do a sort of a wider deployment of robots in the T3 funding period, and for that to be realistic, the operational staff really need to have some of the visualization tools that and the insights that we've been talking about today. So what does that break down to? I guess it breaks down into sort of 5 or 6 key areas. The first one is component trending. So that's making sure that expanding the number of components that we are able to automatically identify and track the condition of those with reliable trending data. The second point is visualizing that information. So just as an example, we can have scenarios where we might have 800 to 1,000 of the same connectors within a hall environment. And obviously that creates some challenges in terms of how do we visualize that in a way that's meaningful for operations staff. So we're spending a lot of time looking at the and creating the visual tools that are needed to allow quick and easy identification of any issues or trends that are that we're seeing within the hall. The next element to that is data exchange. So that is clearly a lot of the condition within the halls is strongly affected by the load. So understanding what load is going through the hall and then being able to factor that into the trend analysis that we do is important. Obviously, the higher the load, the hotter the components get. So the load is important. That means that we need to have the ability to both import and export data, as part of this solution. A dashboard, so a centralized interface, which again gives a one-shot, very easy view for operations people to make sure that everything is running properly. And finally, working on the alerts to ensure that we're producing, first of all, the right number of alerts, that it's realistic for an operations staff. I think we'd had one scenario where Kevin, who is incredibly patient and supportive of us, came back from a few days out of the office to something like 300 or 400 alerts, and so clearly making sure that we that we configure those alerts at the right levels, and that we're doing it for each of the for each of the sort of the mediums that we're tracking. So that means thermal, acoustic, UV, environmental as well. That all of those elements are covered. I guess the sort of the final point that I would make, here, is that we spoke a little bit about the difference, I suppose, between condition monitoring, which is really telling you what's happening today, and that's where our focus is at this point, and then predictive, which is being able to tell you what's going to happen. That obviously is the sort of the ultimate goal, for this kind of project. Where we can start to say, that components that previously, so something like a capacitor as an example, that historically the expectation is that a capacitor just goes bang, but the hope here is that we can, by combining the different data types that we're collecting, by looking at the environmental conditions, analyzing the thermal profile and the acoustic profile of equipment against those environmental conditions, and even looking at visual or optical data. So in other words, with something like a capacitor, is the casing bulging? It's an example that all of those things, give us the potential here to start predicting failures, and that obviously changes things completely. I think that's, if we just go on to the next slide, I think we'll find that's okay. So that's pretty much it. I'll hand back over to Peter.
Well, thanks, Dom, and thanks, Marcella, for taking us through that. It's really insightful, and it's great to see the progress that we've managed to make in just a short period of time, and also to lay out the plan in terms of how we see this development continuing, and how we can gain further benefit from it. There's now a chance to ask any questions around the room. I don't see any messages or questions in the chat, so I guess if anyone has any questions, they can raise their hand, and then we can allow you to ask questions. Nothing from anyone. That's okay.
We are still here, Peter, just in case you think you're talking to an empty room.
No worries, thanks. That's okay. If there's anything that does come up, any other questions that pop into mind, my email address is on that slide there. You can also reach out through any of the social media channels, and with this we shared on LinkedIn. You can get in contact that way, or through the SSEN Transmission Innovation page. There's contact details there as well, if anybody wants to reach out. Alex, you've got your hand up, I think.
Sorry, just see there's a question from Lewis Chambers about what cloud platform or cloud model you're using for data analysis.
Take something there. Yep. Well, it's one that we're developing in-house. So we've got a team of 2 very smart cookies who are developing these for us. The engineers aren't on the call, so we can't give too many details. But they're it's homegrown, using a couple of some open source models, but it's combining things like image and pre-processing, potentially to pull out some of the details, as well as some image augmentation, so that we can get extra examples from a limited data set, and then several layers of, this is team uneducated answering this question here, several layers and combinations of different models to get the output that we want. And also we're envisaging that potentially the models that we've created, that will train them for different component sets. There might be some models that will work for multiple components, but some that are harder to spot may need a different approach.
Marcella. I think, Stephen, you have a question?
Yeah, just a couple of easy ones, really. The slides, will you be sharing those afterwards?
Yes. Yes.
Thank you. Second one, you said about the alpha phase and the, I suppose, tender proposal for supporting on that. Is that out, or is that something you're actually actively working on? And is that going to go out by Jagger and the usual platforms?
So we are currently working on the SIF alpha phase bid at the moment, which will be due to be done by end of next month, and we're just working on that with Ross Robotics at the moment. So we're not intending to put any tenders out for that, for the SIF alpha phase.
Right. Okay. And I suppose that leads into a third question then. From an assurance perspective, how are you assuring your program to ensure that what you think you're getting, you are actually getting?
Well, we do that through, we have the, I'm not sure if you're familiar with the bid process, but it's quite robust in terms of the assessment process that goes through both internally at SSE and Transmission when we're preparing that bid, but also then by the regulator as they're reviewing it to make sure that we're being innovative, we're looking at solutions that are scalable, and also things that provide consumer value. So we go through that process, and then again, anything that's actually intended to be rolled out, like the procurement of robots, for example, go through a procurement process as well.
Yeah, sorry. What I was more looking at there is that when you're actually working with Ross, and this isn't a slight on Ross at all, this is more about the assurance program behind the robot. What you think you've got. Are you getting the right interpretations out of those as you start to go into the machine learning? Are those learnings actually repeatable? And is there an independent review of that process going on to give you, as the end user, the surety that you're looking for?
Yeah, I'll take that. So there's an assurance process within SSEN, so we'll engage with our internal stakeholders, technical staff, our asset management team as well to have that technical review. There'll also be part of this is very IT based, so there's a whole sort of cyber assurance processes that we have to go through to validate and making sure that we are adopting the correct procedures within SSEN with our data. So there's the technical side, the cyber side as well, and obviously we've done a huge amount of risk assessment throughout this whole process as well to implement the robot all through the Network Innovation Project, the NIA project, to get to this point here. So there's been a huge volume of work just in terms of assurance to even get to this point.
Okay, thanks so much, Kevin.
I'd just add to that the robot itself, I mean, in terms of the actual performance of the robot has to be a combination of the sort of the highest levels of industrial immunity combined with pretty much domestic levels of emissions, because whilst it has to survive that environment, it also we have to be sure that the robot doesn't impact the environment that it's working in. And as such, it's gone through a very detailed and extensive certification process, independent certification process as well, to ensure that it's safe and certified to be deployed in those environments.
Thanks very much.
Thank you. Any further questions before we wrap up? See any more questions in the Q&A? No more hands up. Perfect. Like I say, if any other questions come up, do feel free to reach out through any of the channels that I mentioned. But other than that, I just want to say thanks to everyone for your time and attending the call today, and enjoy the rest of your day. Thanks.
Thank you, everybody. Thank you.